Subtracting binary numbers. Now, for subtracting binary numbers, we sometimes use the word 2's complement. This is subtracting binary numbers. Now, it's odd to call it 2's complement because there aren't any 2's in it at all, to be honest. Well, that's the shorthand. I often see it written like this. We've got binary numbers like this with our columns. And we can count up. We can have 0 or whatever we want. But if I did this particular number, if I had this number, to the 4255, right? If I had that number 255, it could be 255 or it might be minus 255. I need negative numbers or I can't subtract. So if I add a positive number to a negative number, it's the same as subtracting one positive number from the other. I need some way, my expression way to work out, is this a positive number or is this a negative number? What we're going to do is we have to decide something is going to flag up positive or negative number. In my simple example, I'll take the last bit and I'll use that bit to flag up a positive number or a negative number. So instead of this representing a number of up to 255, it'll represent slightly less than that, 127, but it could be plus 127, 0 or minus 127 because I've lost that bit. Now obviously in a real system there's a stack of a load of bits to play with and we're not restricted to very small numbers, but there will come a point somewhere we've got to roll over and it's going to finish. And in some C programming, if you've got a set number and you add it and add it and add it and add it, rather than just going back to 0, you'll add a number, get to a certain big number, you'll go to the negative number and start wrapping round and round again. So you can find this in some programming. So, fair enough. If we've got that system, how can we convert the numbers? For this simple exercise, we'll use 8-bit numbers because it's not going to use too much whiteboard space, and we'll convert positive numbers to negative numbers and see what's done. Very, very simple rule. First, we need a number to work out with. Got to have all the leading zeros. So if I had the number 5, got to put these zeros in. I've got enough of them. Or you keep your columns straight, we go nuts. 1, 2, 3, 4, 5, 6, 7, it'll work okay. The first thing I do is swap the 1s and the 0s. So if it's a 0 it becomes a 1 it becomes a 0. Not a good start. Can't go far wrong with that. Next I add 1. So we better have a... Just draw a line so I don't go insane. There's 1. Do some straightforward maths. 1, 1, 0, 1, 1, 1, 1, 1. That wasn't too hard. So in theory, that was 5, and this is minus 5. Of course, how can we be sure he hasn't just made it all up? We can find out by adding 5 and minus 5, because 5 plus minus 5 equals 0. So let's try that out. Bit of space to work with. So minus 5 we think is 1011, and then 4 ones. We thought 5 was 0101 with 4 zeros. Let's see what we end up with. 1 plus 1 makes 10, carry 1. 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 Pause for breath. 1 plus 1 makes 10, carry 1. 1 plus 1 makes 10, carry 1. 1 plus 1 makes 10, carry 1. And 1 plus 1 makes 10, carry 1. Now we've got 8-bit number, the last one we lose. It's going to fall off, we can't with it. So we've worked out, surprisingly, that if we add 5 to that's minus 5 to 5, I end up with 0, because that's all the zeros are. So this must be minus 5. Simple pattern we know now is that if, with 2's complement, the first digit begins with a 1, like so, that's going to be a negative number. If the first digit begins with 0, like so, it'll be a positive number. And what we knew before, if the last number was a 1, it was odd. And if the last number was 0, it would be even.